Hey, welcome back to your favorite calculus class. We're going to take a look at one-sided limits today. So up to this point, we found overall limits, in other words, two-sided limits. All right, and we say, well, the limit as x approaches c of some function is L, even if it's undefined there, as long as they agree that they're approaching it, right? As you approach it, as you get arbitrarily close, if you're agreeing from both sides. This is our informal definition. Then we say, sure, the limit is L, whatever that L is. So in this section, we're going to talk about one-sided limits. So if a function fails to have a limit, it may possibly still have a one-sided limit. Let me give you an example that we looked at in one of the other videos. Here, you obviously, as you approach 0 from the right, if I'm looking at the limit as x approaches 0, from the right it's 1, from the left it's -1. This does not agree. So for this function, the overall limit does not exist. Now, what if we just look at one side instead? Let me denote that. So the limit as x approaches 0 from the right of this function. Okay, that means from the right. So I'm going to follow it, right? As I get closer and closer to 0, right? I'm picking values closer and closer to 0. Am I approaching, getting arbitrarily close to a y value? Sure. It's 1, even though it's undefined there. So I do have a one-sided limit. Now, from the left-hand side, the limit as x approaches 0 from the left of this function, right, as I follow it from the left, it's approaching that y value of -1. Okay, so we have different right hand and left hand limits. So, in fact, let me skip to this right here. We only have an overall limit as x approaches c, if and only if the left hand and the right hand agree, right? In other words, they're going to the same spot, then sure you have a limit, but the left hand and the right hand limits have to agree. All right, let's look at this here. So this function right here has notice it has a right hand limit. It's L as we're approaching C, right? Limit as x approaches C from the right is L. Limit as x approaches C from the left, right? From the left on this one, you got to come from the left is whatever that height is, M. Right? So that one has a left-hand limit. This one has a right-hand limit. This one has the left-hand limit. All right, how about this one? Limit as x. If I was to look at -2, which sided limit would I have to have? I have to approach -2 from which side? Well, it's only defined from the right-hand side, so I'm going to approach it from the right. So for this function, it does have a right-handed limit, right? As I follow it, in other words, as I'm picking x values, getting closer and closer and closer to -2. What's this y value going to? 0. How about if I'm examining the limit as x approaches 2 from the left, because this thing is defined from the left, right? I got to follow it from the left, follow it from the left. And it's approaching a y value of 0. All right, so again, that's an example of a one-handed limit. Let's do some more here. A, limit as x approaches -1 from the right. Is this true or false? Limit as x approaches -1 from the right is 1. So here's -1. We're going to approach this. We're going to follow this function from the right. Is it 1? Yes. Sure enough, it looks like it's approaching 1. True. All right, B. Limit as x goes to 2. Now notice this thing is an overall limit. limit as x goes to 2, so both sides have to agree. Let me approach 2 from the right. Let me approach 2 from the left. Do they agree? Do they go to the same spot? Yes. The limit as x goes to 2 of this function is 1. So this statement right here is false. It's not true that it does not exist. The limit is 1. It agrees. Even though it's undefined, we don't care it's undefined. It's getting arbitrarily close. All right, C. Let me go a different color here. Overall limit here. Limit as x goes to 2. So from both sides as I approach 2, of the limit is 2. No, we just said from both sides our limit was what? 1, not 2. The functional value, f of 2, that's right, that's 2. That's 2. The functional value is 2, but the limit is not. That's false. The limit's 1. D. Limit as x approaches 1 from the left. Okay, here's our x value 1. We're going to approach it from the left. We approach it 1 from the left. What do I get? 2. It's approaching a y value of 2. True. Let me clean this up, you guys. I make such a mess here, don't I? All right, E. Limit as x goes to 1 from the right is 1. So here's my 1. I'm going to approach it from the right. Is it 1? Sure enough, it's 1. True. E is true. F. Limit as x goes to 1. This is an overall limit. Does not exist. So it's got to agree from the right. We know from the right it's 1. From the left, though, it's 2. See the gap there? So limit does not exist. That's true. G. Limit as x goes to 0 from the right is equivalent to the limit as x goes to 0 from the left. So let's follow. So here's an x value 0. So I follow from the right, follow from the left. Do they agree on getting arbitrarily close to the same thing? Yeah. Their limit's 0. So the overall limit also exists. All right, H. Limit as x approaches C of the function exists at every C in the interval from -1 to 1. So this is saying the limit exists every time. So for two-sided limits everywhere from -1 to 1. So it doesn't matter where I'm looking, they gotta agree. They gotta agree there. They gotta agree here from both sides. From both sides, it's 0 from both sides. In other words, there's no gaps, right? Is this thing have no, it can be undefined as long as it's just a hole, but it appears, if you will, to be continuous. And sure, that's true. Now, if you say the same thing but go from 1 to 3, so on I, now I'm thinking about this from 1 to 3. Let me erase a little bit here. Oops. Okay, now I'm going from 1 to 3. Does the limit exist everywhere? Yeah, it does. Even at 2, even though it's undefined, it still agrees. So that's still a true on that one. Now, if they would have said from -1 to 3, that would have been false because we know there's no limit right there at 1. All right. But again, H and I are true on that. All right. Limit as x goes to -1 from the left is 0. Limit as x goes to -1 from the left. Well, you can't approach it from the left. There's nothing over here. All right, that limit does not exist, so that's false. Limit as x goes to 3 from the right. You can't approach it from the right. It does not exist. So that's got to be true. It does not exist. There's nothing from the right. There's not defined there. All right, how about can you do this stuff algebraically? Yeah, you can. So if you're approaching -2 from the right, you have x values. So even though if you plug in -2, we know if we plug in -2 for x, right? This thing's undefined. So I can't just substitute it in. But what I can do is I can think about the absolute value here of x plus 2. Remember, the absolute value of x plus 2, in fact, let me go back to the old absolute value. Absolute value of x, that's an x, just not very good one, is x whenever x is greater than or equal to 0, and it's the opposite of x when x is less than 0, right? We have our absolute value here, and draw it very well, it goes to 0, 0 right there. Okay, so it had two cases, if you will. So the absolute value of x plus 2 is x plus 2 whenever x plus 2 is greater than or equal to 0. In other words, x is greater than or equal to -2. Or it's the opposite of that. Whenever x plus 2 is less than 0. In other words, whenever x is less than -2. Well, if I'm approaching, whatever this function looks like, if I'm approaching -2 from the right, I'm picking when the x values are greater than or equal to that -2, right? I'm picking this case right here. So the x plus 2, just the regular old x plus 2, because I'm coming from the right. So I'm going to use the case 1, if you will. So this becomes limit x goes to -2 from the right, x plus 3 times, I can now drop the absolute value and just use regular x plus 2. And notice, it simplifies, so it behaves like x plus 3, and now I can substitute the -2 in. So -2 plus 3 is 1. So it approaches 1, but now I have a function that it behaves exactly like, since I simplified it, but I can substitute it in. It's now defined there. Now, if I'm going to approach it from the left, now I got to use this case because I'm going to be picking x is less than -2, right? So it becomes limit x goes to -2 from the left of the opposite of x plus 2 over x plus 2. Now those gone, but I got that negative, which means I got to distribute it to the x plus 3 there. So now I got -x minus 3 as I plug -2 in. So -2 now goes in right there. So -2, oops, minus 3. So I got 2 minus 3, I got -1. Okay? So that's how you could do that thing algebraically. It's kind of nice to have those graphs, so you could punch it in decimals.com, take a look at those if you'd like to. All right, so what about when you have these oscillations? We talked about if it's oscillating, there's no limit. Same thing if from a right hand or left hand limit, it just continues to oscillate, and so you never get arbitrarily close to anything. So no one-sided limits here as x approaches. Whoa. As x approaches 0 from the right of this function does not exist. Right, as I get closer, it just keeps bouncing up and down. Right, it doesn't ever get arbitrarily close. Now this function is kind of a unique. This sine theta over theta. In fact, let me give you a picture of it. It's right here. So the limit of theta going to 0. Well, you know what? Let me do this with x. A lot of the time you'll see this with x. Everybody seems to love x. Either one of these is 1. You see how as we approach it, both sides here, the overall limit is 1, even though it's undefined, right? I can't put 0 in for x or 0 in for theta or whatever you're using here because I got a 0 on the bottom. And by the way, this is proved using the sandwich theorem. But keep this in mind. We can use this for an application for problems, applications and problems, algebraic approaches to finding some limits. Okay, here's an example of that. So I'm going to keep in mind the fact that the limit as x approaches 0 of sine x over x is actually 1. Keep that in mind. And I'm going to see if I can apply that. Right, so I'm looking at this and I'm like, well, gosh, this is not, this is the limit as y goes to 0. This would be fine if I had if this was all the same thing. Like here we have x, 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 right? I'm thinking about, I'm like, wait, all those got to be the same for this thing to work out. That doesn't make any sense. So first of all, let me say that if I was to put in 3y, it's the same thing. If 3y is going to 0, it's the same as if y is going to 0. You're just approaching it faster. If you want to think about like a table of values and plugging some y's in there, it's just going more rapidly because you're taking the y and you're multiplying it by 3, right? As you're approaching it. So it's 3y approaches 0. So that makes no difference. So, but these do have to be the same. Okay. So I'm going to leave it right here for a minute though. Limit as y goes to 0. And what I'm going to do is I'm going to think about this. I'm sorry, 3y. I'm going to try and get that. How do I get that to be 3y? How would I do that? Algebraically, I'd say, I'll just multiply by 3/4. But I can't just multiply the bottom by 3/4 all of a sudden. I got to multiply the top by 3/4. Now this does not go into the angle there. That's got to be out front. So this will become, 4y times 3/4. That gives you a 3y on the bottom. That's what I want. Now on the top, I got 3/4 sine of 3y. Now see this. That's like my x, if you will. Here's my x, if you will. Here's my x. So I have limit as x goes to 0 of, do you see it right here? Sine x over x. What is that? That's 1. Okay. And then I had this 3/4 right there, which is right here, which I don't know why I had 3/3. Sorry, that's 3/4. Okay, so let me rewrite this with the properties. I'm going to put the 3/4 out front. That can go out front. And then I've got limit as 3y goes to 0, sine 3y over 3y, right? Again, this is just that 3y is just a quantity. Quantity, 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 right? It fits the bill, if you will. So this is all 1. So I have 3/4 times 1. So I just have 3/4 there. Okay? Thank you so much for listening. That's a nice little overview of some one-sided limits. We'll see you guys next time.